Hello, everybody. This is Professor Ma, and this section is on the Arcland formulas and the surface of revolution formulas. Okay, and these are the two formulas. Okay, and let's one glance at the formula, and there's these components in the formula. Okay, and that particular components, you will see actually shortly, is that actually it is a short segment, short line segments that replaces the curved segments. Okay, it's a line approximation of a small piece of curve. And this is how we do go about it. So here I have a function from A to B, and I want to find the curve length. So what I do, I cut into like before, just like we did for the area, for volumes. We're going to cut the lines and the curve into pieces. How? By taking a partitions from A to B, and then I have corresponding points P1, P2, P3. Corresponds to the partitions x1, x2, x3. Okay, and then after that, we going to do is we're going to, instead of calculating, we're going to calculate the line segments. Okay, and in particular, a line segment connecting from the point pi plus pi or pi to like pi plus 1, if you like, and we're going to use, in particular, use the line segment to approximate, say, that little piece of curve. And then the entire curve length is approximated by using these what we call rectilinear or piecewise linear functions. Okay, and then we're going to take delta x go to 0. So we're going to take these approximations, and the points gets closer and closer, and then we're going to apply the fundamental theorem of calculus, then change the integral, change the summation to integral. So we're adding up these curve lengths. Okay, so each square root it's a length from one point to the other. Okay, and we want to add them, right? And so in particular, here is the algebra. If you pull out the delta x, and I can reformulate by putting the delta x outside. So one of the aim the algebra is put one copy of the delta x outside. But when you do that, you get these. Basically, is derivatives. Okay, as x goes to delta x goes to 0. Okay. So we want to sum up all these segments. Okay, and as delta x goes to 0, then each ratio goes to a prime of x. Okay, so and so then the entire sum on the fundamental theorem of calculus turns into integral. The integral of what? So turns into integral of 1 plus the f prime of x squared dx. Okay. Actually, this is very simple. What it is saying over here is this. Suppose here's a curve. Okay. And suppose here is delta x. And here is delta y. Okay. And what it is, I will come later. And in particular, so here's we're going to calculate the straight line distance. Okay, using delta x and delta y. This is f of x. And at a point, I say here, I can take the slope of a point f prime at x. That's a middle point. Okay, let's call that middle point x star. Okay, I can take that as approximate slope of this red line. Okay, in particular, if that's a slope of the red line, then delta y is going to be f prime, the slope, at that point times delta x, right? Because if the slope of the red line is this much, then delta y has to be this. Then by Pythagorean theorem, the length of that piece is delta x squared plus f prime of x star delta x squared. And I can pull that delta x out. That's exactly what we did. Okay, f prime x star squared times delta x. Okay, so in other words, these little expressions here is actually the length of that little piece. As delta x go to 0, by fundamental theorem of calculus, then we're adding up these little line segments, and that becomes the integral of it turns into an integral. Okay, so that's the significance of that 1 plus square root of f prime squared. Okay. It's a approximations of the length of these items here, right there. And we're adding them up. Okay, good. So it's not difficult to obtain the formula. Well, the difficult part from here is not too many formulas we can actually integrate these. If I just come up with a formula f of x equal to x squared minus 3x divided by x or something like that. I can integrate this if you put into the formulas. And so the problem we can practice on in this using this particular formula, this arc, we'll call this the arc length kernel. Okay, the arc length integral. So in particular, the algebra there are a couple of types that we are going to go through that actually works out in the algebra. Here's one of them. You probably say 2/3 power. That's kind of strange. Why not? Why not? Like what half power? Why 2/3? Oh, that's because of the way the algebra works out. If I calculate the what's inside the square root, okay, let me calculate 1 plus the derivatives, and it turns out that if I put into a fractional form, it just happened. I can then take the denominator outside, okay, 1/9 x to the 2/3. Oops. Okay, and x to the 2/3 comes out. I write it as x to the minus 1/3 in the denominator, right? Why? Because it just happened now. I can use substitution method. This is the u, and just happen the denominator come out is the u prime, right? Derivative of x to the 2/3 is x to the minus 1/3. And so it just happened that something can be pulled out, and the substitutions, the things pull out, we can use substitution and to continue with the problem. Okay, and I'll leave the algebra for you to check if this comes out and put the numbers in. Okay, so that's what a 2/3 powers up there. Okay, on the homework, you'll see quite a few of these strange powers, and that's the reason, because you can pull these tricks out. The other exponents, they don't work. Then you wind up with a problem you can't integrate. The second type of problems that it works out is that when we calculate a square, remember we're trying to calculate this algebra. You have to take the derivative, and you have to square, and then you have to deal with it, integrate these things. And the second type of problem that works out is after you go through this calculation, this actually is a perfect square. This actually turns out to be somebody's square, and actually then this pops out. You just integrate whatever that thing is. Okay, so you probably notice why is a strange fourth power and minus second power. Now that's because when I do this algebra, here's the algebra, you take the derivatives and 1 plus f prime squared, and you square that cube and minus third power. It just happened, everything cancels out nicely and it gives you a minus half in the middle. Where are we going? 1 minus a half is plus a half. And that's a perfect square, okay? And that's what makes these problems work. I mean, you know, it's a one little trick, and then, you know, it works for certain form of formulas like these, kind of like positive power, negative power with strange coefficient. It works out just perfectly. And this one, I can take the square root, right? And the square root just comes out, and then I integrate it. Okay. Now, surface of revolutions. Now let me explain where this formula came from. Okay, if you go back to, let me go back to screen share. So new share, I'm gonna change to the new ones to this one. Yeah. If you go back to the sections on surface of revolution in the beginnings, we have a formula for the rostrum. For the band surface of this rostrum, okay. This is yellow. This surface area, yellow area, okay. It is the small radius on top plus the big radius on the bottom. Okay, these two add them together, and times L and times pi. I'll leave that to you to find out how is that, why is that so. Okay, you can, there are many ways to do this. Not say this. Okay, oops. Okay, let me go back to the screen. Okay, that's back to here. And then here's how that works. Basically, again, we're going to replace this curve by line segment. Then as I follow a line segment, as it spins around, I want to find out the surface area. So I use that straight line segments to spins and it form a rostrum. Okay. And what's the length L? The length L is dx down there before. Okay, this is dx. The length L is this part. Okay, and then what's the big radius? The big radius, is, of course, is this f of xi plus 1. I mean, I plus 1 is the I plus 1 point in the partitions of the x-axis. And then, of course, the small r is the other side, is f of x of I. Okay, so that's this little r, this is the big r of the rostrum. As this line spins around, right? So the surface area of this is 2, is pi f of xi plus f of xi plus 1x1. Pi times L, okay, R times L, okay. But times 2 pi, okay. Then there are two of these, R plus L, going back to, so the R plus L basically become twice of f of x, okay, in that formula. And if you're asking where that 2 come from, is because as delta x go to 0, little r and big R are the same, and they are equal to f of x. Start somewhere in the middle. Okay. So this is the reasons we have these line segment length in the formula for the surface of revolutions. Okay. It is the length of the side of the rostrum. So again, the formula to integrate these is not easy, okay? And we have to make up problems to make things works out. That is, so here's a problem that, again, it's actually 1/2 works out. And so if spin, it forms this parabolic cone, okay? Cone based on parabolas. And then I want to integrate f of x is Ux and Ux squared, Ux prime squared. Okay, so in this case, I can actually multiply the x in the front into the formulas. And when I do that, okay, when you check the algebra, when you do that, you get a linear function, which I can integrate, okay? That becomes an easy substitution. So this is what the answer for that is. So yeah, that's it. This is basically arc length and surface of revolutions, okay? Most of the problem is another applications of fundamental theorem of calculus, and most of the problem you'll see will have these types of algebra that works out. One of the other types of algebra. That is, you can take the square root out of it, or you can substitutions and works out perfectly. That's it. Okay, bye-bye.